Good morning and once again welcome to my YouTube channel Pearson and Excel International Maths by Mr. Kamoto. And in this video I want us to understand something in topic number 8 of Pure Mathematics 1, which is differentiations, and I want us to directly go to example number 1. And we are told that the diagram shows the curve with equation y is equals to x squared. And the diagram looks like this. Y is equals to x squared. The diagram looks like that. And we have a point A whose coordinates 1, 1. And at that point we have a tangent. We have a tangent and within that tangent T, we have another point P here, and it's joined to point A, which means a chord. That is a chord. The most accurate diagram is here. We can look at it and so that we can understand it further. And as you can see, there is a point A1, 1. And if you were to spot another point along tangent T, it will be point 2, 3. This one is a perfect point, x2, y3. So we have a point 2, 3 there. Then the question is, the tangent T to the curve at the point A, 1, 1 is shown. Point A is joined to point P by the chord AP that we have understood. Calculate the gradient of the tangent T. That is part A of the question, the gradient of the tangent T. And you know, the gradient, as we know it, is the change in y over the change in x, which means y2 minus y1 over x2 minus x1. That is when we are dealing with a straight line. And if we take this one to be x1, y1, x2, y2, so the gradient becomes y2, which is 3 minus 1, all over x2, 2 minus 1, 2 minus 1, which is 2 over 1, and it is a 2. That is as far as part A is concerned. But let us just look at part B, which says, calculate the gradient of the chord AP when P has coordinates 2, 4. When P is having coordinates 2, 4, calculate the gradient of the chord AP. And of course, now we treat P just like the way we treated this point, call it point Q, 2, 3. And the gradient of the chord AP, again, it goes without saying, it's simply the gradient is the change in y, and y2 happens to be 4, 4 minus 1, because we are dealing with the chord AP, all over 2 minus 1, which is 3 over 2 over 1 rather, 3 over 1, which is a 3. That is part B, Roman 1. The gradient happens to be 3. Now, when P happens to have different coordinates like 1.5, 2.25, then the gradient of AP, assuming now P approaches A, because the coordinates 1.5, 2.5, somewhere there, we could have a new P there approaching A. Of course, the chord now, the gradient of that chord AP becomes y2, 2.25, minus y1, which is 1, all over x2, which is 1.5, minus x1, which is 1, and this is 1.25 over 0.5. Let us see what that is. 1.25 divided by 0.5, and this is 2.5. The gradient happens to be now 2.5. And part 3, we are told that what if the coordinates of P now changes to be 1.1 to 1.21. What is the gradient? The gradient happens to be y2 1.21 minus 1, y1, of course, a doesn't change, all over 1.1 minus 1, which is 0.21 over 0.1, and the gradient is 2.1. You can already see as P approaches A, the gradient approaches 2. It approaches that of the tangent of the curve at A. And I want us to just directly go to part 5 of equation of example 1, whereby P now happens to be 1 plus h squared. So the gradient happens to be y2, 1 plus h squared minus y1, which is 1, um, all over 1 plus h minus 1. And it goes without saying, if you open this bracket, you're going to have 1 plus 2h plus h squared minus 1. If you open this bracket, of course, you have to bring in minus 1 on board. 1 plus h minus 1 is a h. And at that point, we realize 1 minus 1 is 0. So we have 2h plus h squared all over h. And of course, you realize that h is common at the numerator. We have 2 plus h all over h. And then that h cancels with that, and the gradient happens to be 2 plus h. Now, this is very important because as h approaches 0, meaning that the distance from A to P along the x-axis approaches 0, then the gradient approaches 2. This is just one way to prove that the gradient of the curve is equals to the gradient of the tangent at the point of contact. And of course, let's see what happens if you attempt to answer part C of the question. Comment on the relationship between your answer to part A and part B. Our answer to part A was 2, and our answer to part B, we started with 3, the gradient is 3, it reduced to 2.5, it reduced to 2.1, and of course part 4 would have reduced it according to the literature in the question. Part 4 reduced the gradient, which we did not work out, to 2.01, and of course now part 5, it's leading us to 2. So what can we say? We can say our conclusion is, as P gets closer to A, the gradient of the chord AP gets closer to the gradient of the tangent. And this is just what we need to conclude. And I think we need to write it here, and we say, as P approaches A, the gradient of AP approaches that of tangent T. We will work around this statement throughout this topic. We will work around this statement throughout that topic. But this is just a way of showing you that the gradient of a tangent is equals to the gradient of the curve at the point of contact. Okay?